Hey everyone, we're about to tackle a huge problem, and I mean literally huge. We're talking about numbers that are so big or so mind-bogglingly small that they can totally break our brains, not to mention our calculators. So the big question is, how in the world do we handle the math of the extreme?
Whoa, take a look at this number. That's 8 trillion. And you know what that is? That's the estimated number of germs in a single sneeze. Yeah, wild, right? Now just try to imagine doing any kind of math with that. It's just messy, it's clumsy, and it is so easy to lose track of all those zeros.
So this brings us to a really fundamental challenge. When our world operates on scales that are this massive, and at the same time, this microscopic, how can we possibly keep our math clean and accurate? It's pretty clear, right? We need a better system.
Okay, so let's dive into our first section here. The plain and simple truth is, our everyday way of writing numbers, it just wasn't built for the kind of extremes we deal with in the modern world.
I mean, just think about it for a second. We're talking about things like the national debt, the global population, or even the distance to the nearest star. These are numbers that are fundamental to our reality, right? But trying to write them out in full, it's not just a pain. It actually makes them harder to wrap your head around and compare.
So, what's the solution? Well, it's this beautifully simple and incredibly powerful system called scientific notation. And I want you to think of it less like a math trick and more like a new language. A language designed specifically to talk about scale.
The core idea here is to just stop counting all those individual zeros. It's exhausting. Instead, we're going to let the power of 10 do all the heavy lifting for us. This lets us repackage these totally unwieldy numbers into a nice, clean, compact format that's actually easy to read and, more importantly, easy to work with.
Okay, so every number in this system is broken down into just two simple parts. Part 1, a number between 1 and 10. This holds all the important essential digits. Then, Part 2, a power of 10. This part acts like a giant multiplier, and it tells you where the decimal point really belongs, basically the number's true scale. And it's this separation of the digits from the scale that makes the whole system so incredibly powerful.
And this right here, this is where the system gets really elegant. Because it uses just one simple little thing, the sign of the exponent, positive or negative, to handle both gigantic numbers and incredibly tiny ones. It's brilliant. The core logic is so straightforward, you're going to love it. For big numbers, anything greater than 1, you use a positive exponent. That just tells you to move the decimal to the right. And for tiny numbers, fractions less than 1, you use a negative exponent, which tells you to move the decimal to the left. That's it. That one simple rule is literally the key to the entire system.
All right, let's put this into practice. Let's take the US population. First thing we do is we create our front number by sticking a decimal right after that first digit. So that gives us 3.257. Okay, easy enough. Now, how many places did we have to move that decimal to get it there? Let's count them up. Okay, it's 8 places. And since this is a big number, our exponent is a positive 8. Boom, simple as that.
Okay, now let's flip it and go the other way. We've got this small number, 0.00764. The process is exactly the same. We move the decimal to get a number between 1 and 10, so that's going to be 7.64. Now, how many places did we have to move it this time? 3 places. And here's the key. Since the original number was small, less than 1, our exponent is negative. So the final result is 7.64 times 10 to the negative third.
Okay, so we've got the rules down. But you might be asking, what's the actual point? Well, let's apply this awesome new tool to a couple of real-world problems, and you'll see how it completely, and I mean completely, changes the game.
All right, here's a classic one you've probably seen on social media. You've got a massive billion-dollar lottery jackpot, and the idea is to split it among the entire population. Now, trying to write that out with all the zeros, it would be an absolute nightmare, a mess.
But just look what happens when we convert it to scientific notation. All of a sudden, that horribly messy division problem becomes a really clean, simple one. We've got 1.3 times 10 to the 9th divided by 3.0 times 10 to the 8th. Right away, it's just so much more manageable.
And here's the real magic. Instead of wrestling with, 15 different zeros, the rules are just so simple. For division, you just divide the front numbers, so that's 1.3 divided by 3.0, then you just subtract the exponents, 9 minus 8. And just like that, you've turned a massive, intimidating calculation into two very, very simple steps. So, what's the grand total? What does everyone get? Well, when we put it all together and convert it back, each person gets, wait for it, just $4.33. Huh. Not exactly the life-changing fortune everyone imagines, is it? In just a few easy steps, scientific notation completely revealed the reality that was hidden behind all those huge, flashy numbers.
All right, let's try another one. This time, we'll use multiplication. Let's say we have a pretty significant number of inmates, and there's a significant cost to house each one. So how do we figure out the total annual cost?
Okay, you know the drill. First, we convert. 2.2 million becomes 2.2 times 10 to the 6th. 25,000 becomes 2.5 times 10 to the 4th. Now, the rule for multiplication is basically the inverse of division, and it's just as simple. You multiply the front numbers, and this time you add the exponents. That's the key difference.
So let's do it. 2.2 times 2.5, that gives us 5.5. And for the exponents, 6 plus 4 gives us 10. The result? 5.5 times 10 to the 10th. In other words, a staggering $55 billion. And think about that. We got to this huge, perfectly accurate number without having to write down a single zero until the very, very end.
So I hope it's becoming really clear by now that this is way, way more than just some shortcut for your math class. This is actually a fundamental tool for making sense of the world around us.
And this is really why it matters. It makes these impossibly large numbers readable. It makes complex multiplication and division way simpler. It also creates a kind of universal language that lets, say, an astronomer talking about galaxies and a microbiologist talking about viruses both discuss scale in the same way. But I think most importantly, it gives us the power to look at some big headline-grabbing number and instantly get a real feel for its true size, its true magnitude.
Look, the truth is our standard way of writing numbers is perfect for, buying groceries or checking the temperature. But it totally fails us when we get to the extremes. Scientific notation is the elegant tool we invented to solve that exact problem, and it just works beautifully.
So I'll leave you with this thought. We've just unlocked a new way to see our world, all the way from the cosmic down to the microscopic. And now the only question left is, what huge, crazy question are you going to use it to answer?